So, good morning, dear, and welcome back. So, you have started watching Mathematical Foundation of Robotics, and in that context, we are discussing execution level control. Now, by this time, it is to be clearly understood that the way we are trying to model robot, the basic idea is how to control it the way we want, right? So, everything starting from inverse kinematics, Jacobian, inverse dynamics. So they are trajectory planning. So they are kind of control. Those are called planning level control. Meaning that at the end of the game, the computer will pass some message, means in the form of stream of data, in if it is revolute type of joint, some timestamp data it will send that is about joint angle, joint velocity, like that. But execution level control assumes that somebody, the master, is giving me those data and how to execute, how to actually move the robot. So that's the paradigm of execution level control. By this time you know, right? So in my last class, I discussed a very important concept, because in this course I can only give you the concept. Things are much more maybe complicated, but if you understand the concept, then other things will be very simple. So my earlier class, I talked about model-based control. Model-based control. The basic idea was that if you know the model, then don't try to control all the entire system, okay, whose model you know. Instead, you divide what requires to be controlled, what are easy to be controlled, with the aim that it should be as simple as possible. Why not even in the level of controlling a unitary mass system? Right? So, like that we ended up, right? So it's controlling like just like this, and then you just made servo control plus kpx x double dot plus, then you made this equal to 0 by defining this control law, okay, minus kv x dot minus kp x, like that. So this is what you have started, and then we apply the critical damping condition, and then you get to root kp as simple as this, so that I will get my control law, and as simple as this. We used model-based control. So far so good. But the thing is, you see, this controller has still some problem. Number one, you will have to have a good model of the system, so that you know, you can divide that these are the things I will control, these are the things I will just update the parameter, number one. Number two, still such controller is state dependent, means the controller which is trying to control the x dot, so-called PD controller, may not control something like force or compliance, right? So for that, we need a controller which will be even independent of all the state parameters, okay? So we are going to study, yes, you are right, that trajectory following control, okay, using PD, proportional derivative first, and then we will further modify it, and why we will know. So listen carefully. So here we are, what we are doing, that instead of trying to control the position of the block, with a force, control force F, okay, which is divided into so instead of doing that, actually what we are trying to do, so this was our earlier control. So we were doing this at t equals to t1, I will have to take my block at x1, t2, I will have to take the block x2, blah blah, like that. So that was my earlier goal. Now we are extending the action of our controller to follow a trajectory of the block, how the block will follow this trajectory, which is nothing but a trajectory here is nothing but a function of time. So instead of, I have now desired, instead of at t1, desired xd, now the xd is a time function, right? Is a function of time. That specifies the desired position of the block at any instant of time. So it's not discrete anymore, right? So this is actually, when I have a trajectory, then how can I control modify the control, model-based control? That is the today's concept, right? So again, say I have a system, okay? So this could be mx double dot plus x dot plus kx equal to f. System is equal to 0 and system with control is equals to f, you see. And I have two state x and x dot. And as usual, I have decided that this will be alpha, where alpha will be m and beta will be cx dot plus kx, so that again my control force will be actually equivalent to, see if you put it here, then mx double dot plus cx dot plus kx equal to m x. So this cancels out. So this is what I want to control, right? So this is now a trajectory. So I have a desired, okay, so I have to control a desired trajectory. So what I have now, desired velocity, desired position, all kind of things. They are a function of time because of trajectory. So somebody actually is telling me that, okay, the block should follow the trajectory. That means I will be having some high-level controller, maybe computer, is computing all this desired value which I required to control. Because control must have desired value, right? That's why you will control, right? If I want to control you, I will have, for example, the other day I gave you the example. Suppose I am trying to control your performance in robotics, then I will have to tell you the control action means I will have to tell you that each day how many hours you should study robotics. But I should have a desired goal. What is that desired goal? If I assume that my desired goal is that you will get a plus grade, then the action will be something. If my desired goal is A, then action will be something. So without desired goal, nothing, no control is defined, right? Control has to be based on actually some desired value. So this is desired value, and who is giving? Somebody else is giving. As simple as this. Okay, maybe high-level controller. So here you see. Okay, so this part actually is parameter upgrading as usual, and this is actually servo control. So this is actually control part, right? Servo control part. So what I am trying to do here, you see. Okay, so this is my servo control part. So I will write f dash equals to. So first I can omit x. It is there. Okay, you must understand. But for simplicity, I am just not putting it t, but it is always there. Plus, and I am defining, so when you have a desired value, and these are actual value, okay, you are getting from the system, then I will have to define error equals to desired value. Okay, so in fact actually I will first write correctly and then I will write incorrectly so that xt. So what is this? Xdt is a trajectory, the desired trajectory, actual trajectory. This is the error, okay, at that as a function of time. So I can now write this minus actual. Okay. Sometimes we write like this, the difference between desired, so that it could be plus and minus. Okay. So this will be again. Okay. Like that. So all this. Okay. So this is 1, this is 2, the entire. Okay. So what I am trying to do here, you see, this I am designing a PD controller. Designing a PD controller. Okay. So I will take action based on error. Okay. So this is my control law which I have designed or defined. So I am not getting from anywhere. Okay. I am an artist. So I have defined or designed this control law. Okay. And since it is trying to control a unitary mass trajectory of a unitary mass system, because so this is as if it is trying to control a unitary mass system. So this is equals to actually f dot equal to this. So this is equals to so taking this here, then what you are going to get so what I have done here, I wanted that my controller should not only try to control the state parameter x dot like that. So what I did, I defined a error term, the difference between desired value and actual value. Actual value will be obtained from sensor. Okay, if it is a motor, we have a sensor, position sensor called optical encoder. Okay, so if it is some other device, we may have accelerometer, position sensor, piezoelectric sensor, lots of other sensory devices are there. Sensor is a must, desired value is a must. Sensor will give you actual value. Desired value will be obtained from your planar computer, right? So you can compute error at any instant time. It's a function of time. I have defined this because now it could be, say, I am trying to control a force, right? So if I have desired force and by actual some sensor, piezoelectric sensor or load cell, okay, that is strain gauge. So this is actual. So I can have error. So error could be in the position domain, error could be in force domain, error could be in compliance domain, error could be anywhere. Okay. In temperature domain, if I try to control this temperature of inside the room, then error will be desired temperature minus actual temperature. Okay. So it is more general. That's why I have defined a term error. Okay, with an objective that I won't have kind of controller which I had earlier. That in my earlier lecture you have seen that you are controlling f dash equal to and you have defined this is equals to minus kb x, and that led to okay. So this is my earlier controller which was state specific, but now I would like to get rid of this state specific controller. So what I have done, I have defined error term, and now I am defining the control law instead of like this. My control law is just like this now. Okay, is it clear, right? Okay, so f dash equals to x double dot equals to, this is the way I have defined. Why I have defined this? Because I want in the error domain, the control law in the error domain should be a second order system with these positive terms. Why? Because throughout several lectures you have studied second order system. So if I try to draw the differential equation, if I solve, and in the error domain instead of in the x domain, not amplitude, the error, if I error versus t, if I try to draw, because this is a positive term, there is a positive term, kp, kv, they are gain parameter, they are positive, okay. So only error will be something like this. This is overdamped, or error could be something like this. This is, say, critically damped, or in between error could be something like this. That is underdamped. So anyway, error is going to die down. Okay, that is ensured. So that's why it's very, very important. Whenever you design a controller, in the error domain, if you can have a second order system, just like this, having this term positive, so it will ensure that the controller will be asymptotically stable. Means depending on the value of kpkv, the stability will depend, but most desired of course will be kpkv value designed such that it should be critically damped. But even other way also, either it will be underdamped or overdamped, but the error in the steady state means virtual static state means at t is very, very large, larger than what you can imagine. That is the concept of asymptotic stability. Chain algorithm also, they have coined similar kind of term, but this term existed in control because control is much more older than subject algorithm. So asymptotic stability means this: at t sufficiently large, the system's error will be nullified. Okay, so far so good. So this is the trajectory following controller. You see, let us try to understand this. So this is model based part, upgrading. Upgrading model parameters, and this is servo part. Servo part, okay. So here somebody is feeding me xd desired double dot, xd dot, and actual x, okay. So that and in case of so that I can have a error domain equation like this, second order error domain equation. Then so kp again, if you have kv equal to 2 root kp, you can select either this or that. Select one, get another one, derive another one from this critically damped situation. So you can ensure that your error is critically damped. by suitably selecting the gain parameter. So this is PD control in the error domain. In the error domain, right? And the beauty of this controller is actually trajectory following controller is this is not only modular in terms of system, it is modular in terms of state. Okay, because if somebody is giving you instead of x, that is what will be the variation of force trajectory. Okay, so what is the variation of force trajectory in the acceleration domain, in the velocity domain, and with time actually, and actual force. If you have these values, okay, desired values, who will give this? Your problem and your solution will give these values. So getting those values, if you just get sensor which will actual give these actual values. We do not write actual, so because only if you write this parameter, they are actual. And then you can end up in designing a controller. Okay, so designing a controller like this, you will end up control law in the error domain, which follows second order system, second order linear time invariant system. Beauty is that by suitably selecting KPKV, you can actually ensure that the trajectory is followed perfectly. Okay, so this is proportional derivative control while you are following a trajectory. Okay, now a more practical issue I'll have to discuss that do my controller required, do my controller has disturbance rejection capability? Do my design controller has disturbance rejection capability? Because this is very important requirement. My controller, another technical term is robust. My controller should be robust. So I need to see whether my controller, which I have designed just now, has this disturbance rejection capability or not, or whether it is robust or not. To understand that, let us assume that now I have some disturbance, okay? F disturbance. So is FD, DIST, to demarcate it from desired. So this is not desired, this is disturbance force. And this disturbance force is very, very common in practical applications, you know, because when my robot is trying to do some job, doing some trajectory, the model, maybe my robot model is not that great, means there are some errors, and then robot is moving with some acceleration. So that may create unmodeling some forces, which is a disturbance force. Or from the environment, means where it is doing the job, some reactive forces which you have not expected has appeared, and those are actually could be disturbance forces, right? So if disturbances are there, then how my controller will perform, we are going to talk right now. So this is servo part again. This is model. Okay. So if I now write, so earlier it was actually perfectly when there was no disturbance, I had error domain equation like this, right? Equal to 0 here. in designing this controller, trajectory following controller, I had this relation in the error domain. Okay, so control law in the error domain. So say this is my control law in the error domain I had. But now this 0 cannot be, because now I have additional force, right, which is disturbing force. Now let us assume this disturbance is bounded. Means disturbance cannot be unbounded, very high, all kind of things. So definition is actually over time maximum, okay, disturbance in that time must be less than some value, say alpha. Okay, and alpha could be a constant. There is a constant. Alpha exists always. I will assume that this is the definition of my disturbance force is bounded. Okay, that means at any time the disturbance force must be less than some constant value alpha, and if this is actually, there exists some constant value alpha, and I can figure out that this is the case of disturbance force, then the solution of this differential equation which will result what? Et, right, is also bounded. So this is a concept of actually bounded input, bounded output, and so-called BO. So this is actually intuitively also, you see, if I have a disturbing force, if I have a large disturbing force which is unbounded, of course my controller will be broken. But if I have a disturbing force which is bounded, by definition of bounded is at any time the maximum disturbing force should be less than some constant alpha, then if I solve with this value, if I solve this differential equation, then Et is also bounded, means it will not be large, because still this will be valid and it will have transient response, steady state response, and it will follow that bounded force, and it will be actually, error will be also bounded. Okay. So this is the concept of BO, bounded input, bounded output. So steady state error. So in that case, I need to redefine in such case, redefine my control law. Okay, so what was my earlier control law? This was equals to x z plus kv plus kp error, right? So this was earlier, right? So I need additional term having another gain parameter attached to it, and accumulation of error term, integration e dt. So this is the definition of my control. Where from I have got? Nowhere. I have just designed it. Okay, And why? Then you understand, and then you will understand where from it is coming. So now it's an art. That's why it's an art. Earlier, my definition of control was confined to that, but now since I have a disturbance force, so my bounded, my controller definition of the controller becomes this, and then again, which will lead to control law. Utility. So if it goes here, so this just like earlier, plus kV this plus kPe plus ki integration e dt will be equal to 0. So this is my control law now in the error domain, right? So what I have done, I have added an additional term. Incidentally, it is called, you see now I am taking corrective action, 3 degrees of freedom now I am taking corrective action with respect to the derivative term of the error, proportional to error, and integration of the error. That's why it is called control. This type of controller is called PID controller. Okay. But why? Why have we done this? Okay. So this is part A, and this is part B. So what have we achieved by defining our control law like 3? We have achieved our error control law 4, right? Now, to actually analyze the control law, we'll actually have to differentiate this. We'll have to differentiate this with respect to time. So if there was no disturbing force, then it was 0. Okay, and so if no disturbing, zero. Then from 4, then we need to analyze in the steady state. We'll give. Now, what is steady state error analysis? This is a very interesting concept, and I must tell you. So, when a system is excited by some external agency, I mean, system is like that. So, it has two type of response, right? That you know. One is called transient response. Okay, say I am giving a state force. Okay, so transient response will be like this, and steady state response means at sufficiently large time, what will be the error in the system is called steady state error analysis. Okay, and this is called transient state, means there will be some error, response time will be there depending on whether it is steady, under-damped, critically damped, or over-damped system. Okay, so this, and after some settling time, there should not be, ideally in a good controller, there should not be any error, which is called steady state error 0. So, and this is analogous to very, very crude example I am giving. Say, when you are taking a flight. So on the runway, it is you are from rest, and in the runway it is running at a very high speed, and then it is taking off, then ups and downs and all kind of things. So this is called transient state response of the aircraft. When you are inside, you can understand lots of turbulence are there, right? But same aircraft, when reaching at say 30,000 feet above, and then after say in a 10-hour flight, after 1 hour or so, then it moves in a very steady state, as if you feel that it is a virtually static state, means you are not moving at all. So steady state actually, error, if steady state error is 0, then in this condition we can call, if you think that it's perfectly static, then we call steady state error of the aircraft when it is following a trajectory. Aircraft also follow a trajectory, right? From one country to another country, there is a distinct trajectory. So if the steady state error is 0, that means you will feel very comfortable, means it is exactly following the trajectory. So steady state error analysis is actually analysis corresponding to virtual static state. Means in the dynamic equation, all the time related term, if you make 0, then what is the error will be the steady state error. So apply the same thing here in equation number 4. So in the steady state, okay, so this is 0, this is 0, okay, and I cannot make steady state analysis in this domain, so I will have to make additional. So it's jumble up, right? I cannot figure out what is the steady state error. To have that steady state error, I will differentiate the same equation 4 with respect to time again. Okay, so this is error triple dot plus kv, error double dot plus kp, error dot plus ki, error equal to 0. Because if you just differentiate this with respect to time, integration e dt equals to e, right? So they are all, this is what, right? And in the steady state, I told you all the time related term has to be 0, right? So steady state error analysis, what is error? Here, ki times e equal to 0, so that takes you error equal to 0. But even if you do not have this term, steady state error in a second order system was 0, right? So PD control, when this is 0, that is no disturbance force, the performance of a PID control and the PD control will be same. Okay, so it will be a very bad idea if you do not expect in the system external disturbance to deploy PID control. Okay, because more degrees of freedom you have, more control gain parameter you have, more costly the controller will be. Now, if there is a disturbance force, then the equation will be like this, right? In the error in the error domain, now I have a disturbance bounded. Now if it is bounded just like this, then I am making a steady state error analysis again. Equal to dot. Now you see carefully, this is the aerodynamic equation when there is a disturbing force, and I have taken it for steady state analysis, I have taken it to another order, I have differentiated that equation with respect to time again, and now I am doing steady state error analysis. So all the time related term will be 0, this is 0, this is 0, this is 0. So what is the error now? Error will be equals to divided by AI, right? So you now see the error is now steady state, there will be some error, is given by this. Now, if my disturbance is bounded and constant, and most of the time if it is due to poor modeling error or it is coming from the environment, this becomes, disturbance force become constant, isn't it? So if you just differentiate with respect to time, this will be 0. So if the system is encountering a constant disturbing force, by virtue of designing, by virtue of putting another term ki integration e dt, which is PID control, you are able to make your steady state error equal to 0 if this is constant, because the differentiation of the constant term will be 0, so this is 0. But even if it is not perfectly constant, then you have another way to minimize the error. By increasing this Ki term will actually, you can minimize the error. But this is not very good idea to increase Ki whimsically. And this is, but philosophically I told you that this is the concept of proportional integral derivative controller. So in the system, if you have, our take home, in the system if you have disturbing force, then you should deploy this kind of control law, which is given by equation number 3. Okay, so that's the reason why the control law has this term, integral term. Now it is clear to you after taking 2-3 steps. Here it was not clear, as if it came from the heaven, right? But yes, the reason is, if there is disturbing force, then our PD control could not handle it, right? If you see now, if you have a PD control, so then you see the plus KB, okay, plus KP equal to F disturbance, right? So if it, you do not need to go here. For steady state analysis, you, in a PD controller, for PD control, what is PD control law? Kp error equal to F disturbance. So, and the steady state, this is 0, steady state error analysis, short form SSEA, steady state error analysis. So this is 0, this is 0, and error becomes your disturbance divided by Kp. So at the most, by increasing Kp, you could minimize error, but in no way you could eliminate error. But by redefining my control law like 3, we have proved that your error would be 0 if the disturbance is constant. Here, if it is constant, again, no, error will be 0, right? But here, if constant, it will be 0. If it is not constant, even then, you have some freedom to make it, to minimize it. So it preserves, PID controller preserves all the facilities of PD controller, but it's one step ahead. But again, as an engineer, you should optimize everything. If it is not required, if you are not expecting disturbance in your system, then go for PD controller, proportional derivative controller. That is sufficiently, it will make. So in the absence of, I have shown you, in the absence of disturbance, the performance of PID controller and PD controller will be same. So then why I should go for PID controller, inviting more trouble? I should not. But if my system likely to experience disturbance force, then I should design a PID controller, and I have proved in that case, if the disturbance is constant, then error, steady state error will be completely 0. But even if it is not constant, by suitably selecting the gain parameter Ki, you can minimize it. However, PID controller now have 3 degrees of freedom, so Kp, Kv, Ki. So for designing stable controller, right, Kp, Kv, Ki values are to be selected properly. Here you cannot just simply put the critically damped condition and crank out Kv equal to 2 root Kp. No. Additional parameter you have Ki. So how to tune PID controller, it's a issue, and there are ways for doing that. But up to this, you understood why we need PID controller, when we need PID controller, when we need PD controller. Okay. So with this, I think I will stop here. can further study our textbook by John J. Craig, okay, and Peter Koch, right? So you can get some hands-on, right? And I hope that the concept is clear, and if it is, then now we are in a position to take you to a practical controller design, and that will be in the next class. Till then, stay safe and have a nice day. Bye-bye.